Well, thank you very much. Mike Hoyer, Applications Engineer for HBK. Maybe you're wondering, what was HBK? Well, HBK about 5, 6 years ago culminated in the combining of two companies that have been around for over 70 years. HBM more in the time domain and offering string gauge based sensors and data acquisition and analysis. And then Brulin Care, also known as B&K, more in the frequency domain, basically offering sound and vibration solutions, shakers, accelerometers, and analysis. And so HBM, B&K, now HBK. So a little bit of history on the HBK name. Myself, I started with a company in high-speed data acquisition about 1991. And here I am, basically 4 acquisitions later. So we're in the world of acquisitions. So, but I'm really delighted and privileged to be an application engineer, which pretty much seems to be the same company I started with, but just ever growing with more solutions for people like you. So this is a great opportunity, and every day is an adventure because every day I see a different application, whether it be in aerospace, automotive, etc., industrial. And so let's get right to it. So basically what our goal is today is to be able to help you make better and quicker measurements in electric powertrains. And we're going to do that by looking at things like EMI. What is it? What causes it? How to conquer it? We'll talk about cabling and sensors and how to mitigate EMI issues for voltage, current, torque, speed, and so forth. And we'll even talk about some things like torque ripple. What is it? I mean, it is another source of noise. What causes it? How to measure it? Harmonics, another source of noise, except instead of mechanical like torque ripple, it's electrical. And what causes it? How to measure it? We'll talk about a measurement uncertainty, very important factor. Why use it? What is it? How to measure it? And then we'll wrap things up with the total measurement solution and how you basically end up overcoming these EMI issues and improving accuracy in your measurement. And then, of course, we'll have some Q&A at the end. So what is EMI, or sometimes known as electromagnetic interference? So basically, it's noise, interference, or electricity from one or more sources interfering with a signal. Probably have experienced in the past something like this. You've got spark plugs, vacuum cleaner, you've got lightning can cause interference maybe with a signal that you're maybe listening to, maybe on an AM radio or on the television. So sources of interference include galvanic, inductive, capacitive, radiation. And so exactly what are these sources and what would be some solutions? Well, basically with galvanic issues, you have the physical connection between points. You also have to deal with ground loops. You've got a path to ground, possibly shorter across another circuit. You also got introduction of noise into the common path from the load. So it's dependent on the cross-section of the wire, the length, and the resistance of the wire. And some solutions include low impedance paths to ground, elimination of ground loops, and some proper grounding. But later on in this webinar, we'll talk about some ultimate solutions to conquer, mitigate these issues. So that's coming up later in this webinar. So we have inductive coupling. So inductive issues, we've got current induced from a current carrier to a single wire. You've got the transformer effect, for example, loops of cable. And it's dependent on the DIDT, the frequency, the current amplitude, the distance, and also the layout of your cables. So the solutions, again, these are just very brief solutions. We'll get a little bit more detail on some of these solutions. And again, we will talk about an ultimate solution, which is rather exciting near the end of this webinar. So we've got shielding is a possible solution. You also want to eliminate parallel paths and loops. You want to make sure that you have a significant distance between the cables and the source, and eliminate copper cabling if you can do so. So capacitive coupling, we've got capacitive issues, charge jumping from one source to another. We've got dependencies, of course, on DVDT, the voltage level, the frequency, the distance, again, between the cables and the layout of your cables. So again, solutions include the shielding, eliminating parallel paths, the distance between cables, and also try to eliminate copper cabling. And we'll talk again more about these solutions in a few moments. And then there's also radiation coupling. So electromagnetic field interference, radiation over a distance, high voltage and high current situations. Again, dependent on the DI, DT, and DVTT, you've got the frequency, the voltage, and the current levels to deal with, and the distance between the cables. Again, solutions, shielding, layout of cables, and trying to eliminate the copper cabling. Now we've also got some additional testing issues in some industry trends that are making things a lot more challenging in making measurements on powertrain measurements. And those include things like higher voltages. Battery voltages are increasing to improve driving range, and some of them are as high as 800 volts and some even higher. So that means you need to have higher measurement ranges. You also have to have higher voltage safety levels, and you want to be sure the power analyzer meets the needed voltage level and over voltage categories. In fact, most automotive test rigs are Cat 3, so you want to make sure your power analyzer is certified for this measurement. Many power analyzers I've seen on the market are only certified for Cat 2 or very limited in levels in Cat 3. There's also higher frequencies that we need to contend with, increased slew rate, which is leading to more EMI emitted and thus increases the EMI issues. You have increased sensitivity for long cables and cable capacitance, which will further limit the bandwidth, and you have increased measurement errors caused by increased cable reflections. So in conclusion, the new powertrain demands are becoming more challenging to measure. So what part of an electric powertrain test is most important? Is it the cabling, the sensors, the recorder, the operator? Well, a chain is only as strong as its weakest link. You've probably heard that sometime or another. That's actually from 1786. I looked that up. I was surprised it went back that far. A proverb from Scottish philosopher Thomas Reid. So basically the answer being they're all important. So it's very important that you address cabling appropriately and you use appropriate sensors, recorders, and that the operator pays attention to all these factors. And we're going to talk about those factors as we move along here in the webinar. So a current powertrain test setup may look something like this. You have got your, on the left, your motor and your inverter, and of course there's a battery driving the inverter. And so you're trying to make measurements on voltage. Unfortunately, it can be very dangerous high voltage, some current. You want to measure torque, speed, maybe some temperatures. So you've got this array of cabling and dangerous voltages and EMI that are pretty much throughout the entire measurement, from the point of measurement all the way back to the data acquisition or power analyzer system. So the ideal world, of course, would be to have a clean setup for these power measurements. And so if that was possible, that would ideally be the way to go. But we need to deal with reality here, and that's why we're all here, is to how to mitigate the issues of the world. So maybe you've set up some of these types of tests and have seen a setup that may look like one of these pictures here, somewhat clean, somewhat very messy. But that's the reality that we're dealing with at times. So basically, what does that lead us to? We've got some dangerous voltages at the power source, and we also have them at the inverter. We also have them in our cables that are going back to the power analyzer or data acquisition system. And so even our automated system or dyno. So you want to make sure that you use Cat 3 equipment so that you are very well protected, not only yourself, but also the analyzer and its input. So you've got EMC issues, of course, throughout the measurement chain. So quite a few things to be concerned about, whether it's the cabling, the sensors, the method in which you connect things to your power analyzer and so forth. And so let's talk about some of these things and how to mitigate some of these issues. Basically, during an electric motor test, you've got the inverter, variable frequency drives, and other electronic equipment generating high energy frequency, which we call EMI, electromagnetic interference. But to help reduce the electromagnetic interference and ensure more accurate measurements, for the best signal fidelity, you want to be sure and keep all the current cables away from voltage cables as much as possible. One suggestion is 3 meters. And it's suggested to keep the mainframe as well, the power analyzer, away from the device under test by at least 3 meters as well. You want to be sure and choose the right length of voltage and current cable, because you want to avoid rolling up the cables. Because when cables are rolled up, you're going to get high frequency electromagnetic interference, which is going to induce more currents and adds noise to the signal. Well, let's talk about the sensor cabling. We'll start there. Some connections I've seen are unshielded measurement cables, and they're basically subject to electrical noise. You got high frequency inverters, pulse width modulated voltages, and it's going to result in basically bad noisy measurements. So you want to be sure and use shielded measurement cables. And ideally, you want to measure the center conductor current, not the outer shield current. And if you were to take the entire cable, the shielded cable, and place it right through the CT, you'll end up measuring both the center conductor and the outer shield. So you ideally would want to avoid that circumstance, but how do you go about measuring just the current in a shielded cable? Well, here's one solution. Basically routing the shield around the sensor and ideally placing the entire CT in this configuration of measurement within a Faraday cage-like box here, and only place the center conductor through the CT, and then the shield around the CT. Here, noise is still suppressed by the shield, and the sensors are in an EMC cabinet. It's grounded, and the sensors spaced to specification. So ideally, you would want to have your DC signals in one cabinet, and then your AC signals in their own cabinet, separated from AC and DC. So that would be kind of a practical solution there. And then connecting from the CT to the, let's say, power supply of the CT, you want to have shielded cable as well. And here we're showing not only shielded cable, but it's also a twisted pair. This is going to create a Faraday shield around the signal, and the shorter cables are preferred. And the shielded cables are from the transducer to the measurement unit. Let's talk a little bit about high voltage. So basically, ideally, you want to use shielded cable there as well, but the cable has to be able to withstand high voltages. You want to have 1500 volt DC Cat 3 cable in most cases, especially with the higher voltages that are forthcoming in the industry. So here we have a cable, 3-phase black, brown, gray, the single phase neutral to line, and a shielded connector, yellow. And I want to emphasize that you only would want to connect the shield, the yellow portion of the connector, on just one side of the cable, not both. Otherwise, you would create ground loops. So essentially, just connect the ground on one side of the shield of the cable, and that way you'll create a nice Faraday cage around the cable to reduce the electromagnetic interference. Here we have another probe. If you're needing to make measurements up to 5 kV, that's a common way of making a measurement on signals that are in the 5,000 volt RMS range. This is a differential probe that matches up nicely with this particular amplifier that's commonly used for HBK customers. And there are different ways to make connections with voltage. There's a HBK offers an artificial star adapter, which makes it nice, quick, and easy to make a 3-phase high voltage measurement. However, it does assume that the system is balanced. Ideally, for the best method of recording the 3 different phases of voltage, it would be ideal to really use a phase-to-phase measurement, or what sometimes is called line-to-line, and that is best for unbalanced systems. Again, connecting the yellow shield just to one side of the measurement. So in this example here, we've got it connected to the mainframe's ground lug. Let's talk a little bit about torque and speed cabling. So a lot of times I've seen users make measurements on analog torque signals, but they're susceptible to noise and EMI, and they do have low accuracy. So ideally you want to use frequency or digital signals, since they are immune to noise and EMI, and they offer a much higher accuracy. So if whenever possible you want to record your torque and your speed using frequency or digital signals with appropriate shielding, of course, on your cabling, mitigating noise, for the highest accuracy of measurement and torque. So for high accuracy, flexibility, and even future-proof, here's some examples of basically making a measurement with torque and speed. A lot of these ones that you see here from HBK are non-contact torque and speed sensors. So the speed sensor is an option that can be embedded within the torque sensor. The most accurate torque sensor in the world actually is 0.007%. That's the T12. Great for efficiency measurements. The best value for the money, if you're looking to make a accuracy measurement of about 0.03%, you've got the T40B. And then on the bottom, a new series we've just introduced offers higher bandwidth up to 15 kilohertz. And not only that, it's excellent for torque ripple measurements, which we'll touch on in just a moment. But you get some nice accuracies, 0.03 and even an optional 0.01% accuracy. But you also have no hub antenna like you do in the other two on the above here on this page, because you actually just have one stator, and that will fit all the range rotors. So that's an exciting new series that we're adding to our lineup for high accuracy, high bandwidth, and flexibility in adding just any size rotor to the same stator. So let me touch on that torque ripple, which is really a mechanical noise. It's an unwanted effect of an electric drive. So various causes like modulation, the method of modulation, or the mechanical design will cause torque ripple. And naturally, it's unwanted. It's going to add increased noise, vibration, and it will even possibly decrease the lifetime of the system. So it's essential to understand how much torque ripple is generated. And the HBK Power Analyzer solution does offer the ability to easily measure torque ripple. It automatically sets up the appropriate analysis equations to do so. And here's a nice little example screen that has been set up where you have torque ripple, which is a small, fast AC component on top of the more static mean torque. So here we have two graphs. The square you see in the top is actually magnified on the bottom graph, where you have the black line is actually the average static torque, but the red signal is actually the torque ripple. And there's an automatic measurement that is made to give you a percentage of the torque ripple based on the total torque that's being measured. In this case, we see it's 10.74% of the 1 Newton meter torque. So this is very valuable information, so you can try to identify means and make measurements and improve your actual motor and your inverter to try and reduce the noise, the vibration, and increase the lifetime of your system. What's really nice here is that we're now showing here on the HBK system, the efficiency map is on the left and a torque ripple map is on the right. So this is going to give you information where a drive might be efficient, but also where it will vibrate the most. So between the two maps, you'll need to decide, where do you want to drive the motor, where it's most efficient, but yet vibrating the least. So these are very efficient maps that are automatically generated for you on the HBK solution. Now, since we were talking about mechanical noise, let's talk about electrical noise. We've got the harmonics of power and RMS that need to be calculated. So why calculate harmonics? Well, in an electric drive, it's of interest to understand how much of the active power is in the fundamental. So you have the first harmonic, known as the fundamental. That's going to create your torque, which makes the motor turn. However, you've got all these harmonics, which create losses and makes the motor hot. So the significant portion of the useful power is transmitted in the fundamental, and a predominant portion of harmonic power leads to unwanted effects and losses. So The same applies to the respective harmonic for RMS current. Here you see just an example of some of the equations that are automatically generated in and they're actually performed in real time. These are for phase 1. And you can see the list on the right for the equations that are, or the calculations that are performed for current harmonics, both for phase 1, 2, and 3, and also for power, the fundamental, and the harmonics, and also the voltage harmonics for phases 1, 2, and 3, etc. So these basically becomes very valuable. And how valuable, you may ask? Well, here's an example of a real-time harmonic power and RMS calculation. So in this example, we took a steady-state measurement of a harmonic active power of a converter-fed PSM at constant total active power independency of the switching frequency of the converter. So basically, what we did is just changed the switching frequency of the inverter. So you can see starting from the left, it was about 3 kilohertz, and then we just increased it to 5 kilohertz, and so on and so forth. But if you were looking at the black line, which is the total power, you would never see any changes with the changing frequency. So you would think that, it really doesn't have an effect when you do change the frequency of the inverter. But if you start taking a look at the inverter total power, the inverter power harmonics and the inverter current harmonics, you do notice a change there. And so what you need to do is take a look at these harmonics to identify, what's going on here. You see that the inverter current harmonics, basically a motor becomes more efficient as you increase the frequency. However, the inverter becomes less efficient as you increase the frequency. You've got inverter losses. So you need to make a compromise there. It's kind of a two-edged sword, but at least you have the information you need in order to make a better decision. In the HBK solution, you have an Ethernet cable that runs between your computer and the power analyzer. And so you want to make sure that the cabling used is not going to have effects from the EMI, the noise. And whenever I get a customer or user that's having maybe an issue every once in a while with the connection between their computer and the power analyzer, I first ask, well, are you using shielded Ethernet cables? So that's the first thing that you really want to consider, is using shielded Ethernet cables, like you see here at the top right, as opposed to what is in the X that's not shielded at all. But ideally, you would want to use a fiber optic Ethernet solution, so that has the ultimate noise immunity and isolation from high voltage and the current environments. So let's go back to this solution we were looking at for a typical powertrain measurement. So we have the high voltages throughout our setup, whether it be at the test point and all the way back to the power analyzer and your test lab. And so here are the problems with a typical setup and the cabling. You've got high voltages everywhere, EMI everywhere, and really the challenge is, how do you mitigate this even after applying all the cabling solutions that we've just looked at here in the last few minutes? Well, introducing a very unique and ultimate method for mitigating, if not conquering, EMI issues. What we have here is what we call remote voltage probes and remote current probes. Even the remote current probe in this case has a optional CT power supply built in. So ideally, you've got very short cables from the measurement point to the remote probe. And the voltage remote probe, let's say, is capturing the DC voltage from the battery and also the 3 phases of voltage from the inverter. And then instead of having that extra power supply and extra cabling to power the CTs, here we've got the actual CT power supply built into the remote current probe. And you can connect the CTs directly to this remote current probe. And both of these probes, voltage and current, are providing the measurement results back to the power analyzer via fiber optic. So now you've eliminated a lot of the high voltage issues back in your lab, the control room, I should say. And then also you have basically isolation and EMI mitigation with this setup, resulting in minimizing or conquering the EMI issues You've got uncompromised safety. You also have independent probe calibration, so you don't need to send your mainframe back for calibration. You just send that remote probe, whether it be a voltage or current probe, and you can maybe have a spare one handy to continue to make measurements, and that makes it a lot easier for calibration. Shorter cables are going to prevent reflections, so you just have a nice short cable that goes from the measurement point to the probe. You don't have to run a wire or cable all the way back to the data acquisition system because you've got that fiber optic link. And the integrated CT, as I mentioned earlier, built into the remote current probe is going to minimize that additional cabling for the CT power. And this distributed setup has a cable length capability of up to 100 meters. So quite a nice solution for conquering, if you will, EMI issues. So basically the remote probe power measurement concept is going to eliminate the EMI back at the power analyzer, and as well as the high voltages. This is kind of how I think of it. A little diagram I created here showing you the high voltage and high EMI in your test cell, but back in the control room, you're completely safe and away from the high voltages and also from the EMI. So a little bit more detail on these remote probes here. What we have is a voltage probe, or as we call it, a remote voltage probe. You've got 5 voltage ranges you can choose from, up to plus minus 2,000 volts DC. So this is going to be able to handle not only the present trend of voltages, but also future higher voltage that are forthcoming. And you also have 4 individually replaceable voltage channels on the voltage probe, and it samples at 2 million samples per second, which is very well sampled. Most of our customers sampling somewhere around 2, 5, no more than 1 megasample. And when I meant 200, I meant 200 kilosamples or 500 kilosamples versus, and also 1 megasample. But you can, basically sample up to 2 million samples per second. There's also an option that we will be introducing that will enable you to sample even faster than that for those who, for whatever reason, may wish to sample faster. But we also have that remote current probe with 7 current ranges up to plus minus 2 amps, again with 4 individually replaceable current channels, 2 built-in precision burden resistors inside. And you also have additional voltage inputs if you end up using a current clamp for just a quick measurement. Again, same sample rate capability. And then we also have the variant, which is the one on the most right, seen here in the diagram, which has a built-in power supply for the CTs. So the fiber optic signals that you would have coming out of these remote probes would then connect to this remote probe receiver, which actually is embedded. You basically slide one of these into your mainframe. You want to make more voltage and current measurements, you just add more probes and more of these receiver cards. But basically, you have a power accuracy of 0.015% of reading and 0.02% of range. And so this is really going to provide you with a lot more safety. And as we mentioned back in here, mitigate your EMI issues and provide you with shorter cables and also minimizing cabling. And you're going to be able to calibrate your probes a lot easier without having to send back also the mainframe. A little note on measurement uncertainty, since that becomes a vital part of your entire measurement. So, for example, you may have heard the statement, a measurement result that does not include an uncertainty of measurement statement is so unsafe you would be better off without it. That's from Werner Richter, from professor of metrology. But you may have also heard that you always measure wrong, you just need to know by how much. And that's from Dave Packard, co-founder of Hewlett-Packard. So measurement uncertainty is very important. And basically, it's a statistical method to understand how trustworthy your result is. It's basically a distribution around a measurement of possible values. You've got systematic and random effects that result in measurement uncertainty, which are represented by probability distribution, which you kind of see here in this diagram. So what you want to do is you want to be able to optimize your test bench. I apologize. I guess the timing on some of these slides was set, and I should have made it set for manual. But actually, you want to optimize your test benches. Basically, you want to base your selection of your equipment and your sensors on the specifications. And some data sheets don't have all the information you have, so sometimes you may need to dig a little bit deeper to research and find out what those specifications are. But you want to use appropriate sensors and amplifiers that achieve a low measurement uncertainty so that you can have a more trustworthy measurement. Unfortunately, measurement uncertainty can often take hours and even days to calculate manually. Here is something that's really exciting that we have introduced just recently. The HBK solution offers the ability to automatically calculate the measurement uncertainty for every set point. This is really exciting. It's pretty cool, actually. So what you have, you've actually got a set point table with all the results, and you can select whatever results that you want to include in the table. It's up to you. But more importantly, you've got an efficiency map on the left, and then on the right, you have a measurement uncertainty graph of the efficiency map. So now you can identify what parts are more trustworthy than others in your measurements. So I mentioned HBK at the beginning. I'll mention it again here. Basically, the nice thing about HBK is that you're not just buying a device that is going to record or monitor your power, your voltage, your current, or what have you. It's actually a tool to help you to improve upon the research and development of your inverter, your motor, and your entire powertrain. And not only are you necessarily just getting one component of the entire powertrain, you have the ability to do what we call one-stop shop. We've got sensors for the torque, the speed, the current, all from one provider, one company. So that way you can basically avoid seeing the result where somebody's pointing left and right. It's his fault. Everything for the entire powertrain can be obtained from HBK. So everything from remote probes for measuring the voltage, the current, and you can choose whether or not you want the CT power supply integrated into the current remote probe. We've got the sensors, as I mentioned, CTs, torque, speed, accelerometers, strain gauges. Yes, you can make all different types of mechanical signals, and physical signals like temperature can all be recorded all simultaneously and synchronously to that one mainframe box. And that comes in very handy. So power analyzers that can handle up to 51 power channels in one mainframe, and all the appropriate I/O for dyno controllers, from EtherCAT to CAN, GenDAC API, and so on and so forth. This is just a brief overview here. A lot of real-time analysis is available, as we've mentioned a little bit already. You got DQ0, space vector, efficiency maps, are all available to you, automatically generated for you, all in real time. Training's available on site or virtually, and of course we offer calibration and service contracts for your system. But those remote probes make it really handy too for calibration, not having to send in the mainframe, just the remote probe itself. But this entire solution adapts itself really nicely for not only automotive, but also for aerospace and industrial applications here in the automotive industry. It's very scalable for component testing to vehicle energy management analysis. You've got, as I mentioned, API. You can do CAN, EtherCAT, XCP for setup and control to your dyno. And you're also recording all the data. The raw data is also stored so that you can do further analysis without having to do the test over again. That comes in real handy. And as I mentioned, it's also very adaptable for aerospace with input voltages up to 5 kV, usable bandwidth up to 160 kilohertz to meet the newest aerospace power quality standards. Very scalable performance to hundreds of voltage, current, and power channels at full sample rate. Data streaming to multiple RAID arrays for the highest throughput for data security, and powerful recording modes, sample rate switching, etc. So, and you can do combined electrical and mechanical testing for eVTOL certification testing. Very handy and adaptable. So that's just a quick overview of conquering EMI, trying to improve accuracy in your measurements through cabling and other techniques. And so I want to thank you for your time. Basically, we have more information available at our website. For example, you can go to www.hbm.com/eDrive. It will give you kind of an overview there as a first step. We also have support emails available, support@usa.hbm.com in North America, and also worldwide at support@hbkworld.com. So thank you very much for your time. Feel free to give us a call, send us an email. We'd be more than happy to discuss your application for variable speed drives and begin providing you with a solution that is adaptable to your application. So it's a very adaptable and flexible system set up whether you use remote probes or not. But the really nice thing is that you've got all these great analysis functions that are built in that are going to eliminate a lot of the time-consuming chores of making measurements on whether it be DQ0 or measurement uncertainty and efficiency maps in real time. That is just going to make it so much quicker for you to complete the research and development of your inverter and your motor without having to spend all those extra days or weeks trying to do a lot of the stuff yourself. So be more than happy to discuss that with you or any of the members in our team. Drop us a line, go to our website. So you can go to hbm.com or you can go to hbkworld.com for further details on any of these solutions. And thank you very much for your time.